report
Okay.
that I'd get 100 on for
Hi,
now,
everybody.
I'd get like a 70 for something.
We can complain about black reports after class. I want to continue on our journey to the hydrogen atom. We're still not quite there yet, and we won't be there today. But the hydrogen atom is complicated. It's the culmination of almost 20, 30, 3 decades of work by the most brilliant minds in science. And we're going to find, and the best part of this result, I can guarantee you, we're going to come up with an exact solution for the hydrogen atom. We'll be able to say to absolute precision, whatever precision we choose, and it ends up being something like 11 or 12 significant digits when you take it all the way, any property of the hydrogen atom. We're going to come up with an exact solution for exactly the way the hydrogen atom functions and looks, operates, you name it. Right? So it's important that we go through this journey because in some ways this is the mathematical foundation of all of chemistry, right? How does an atom arrange itself electronically? Now, we're not going to talk about the nucleus so much. Of course, there's lots of interesting things with nuclei. You start adding protons and neutrons. It's not really the point of this class because chemistry isn't, well, there's nuclear chemistry, of course, right? Radioactive decay and stuff, but by and large, 99.9% of chemistry is just electrons. You don't have to worry about the nuclei too much. And one of the things that we identified last class about the thing that we need to solve is that this is a 3-dimensional problem, and the way that we're going to construct this problem is to break it into 2 chunks. We have the radial part, right? You have a proton. Here I've made it very generically. We have 2 masses. You can think of this as being the proton M2, this big mass. Right? Remember, the proton is 1,000 times bigger than the electron. Right? I've said this a couple times, but if the electron had hydrogen's mass, the proton would be larger than every naturally occurring element by a factor of 5. Right? Uranium has a mass of about 238. 238 AMU. Right? And hydrogen's 1. Right, so the ratio of atomic masses is on the order of about 200 across the periodic table, but the mass of the proton and the electron is 1,000. So the electron is absolutely tiny, and the proton is this giant hulking mass of positive charge. Where was I getting? I'm getting lost in atoms. But anyway, so we have two parts of our problem that we have to deal with. We have a hydrogen atom attached at some distance to a proton. Right, we have the radial problem. We talked about that, right? We have the electrostatic attraction between the electron and the proton, right? And that's only a function of the distance between the two, right? The radial part, right? It's a spherically symmetric potential. It doesn't matter which direction the electron is with respect to the proton's axis system. It just matters on the distance, right? So we have this radial part, which I've kind of put off to the side for now. Got this 1 over r dependence to potential, and we'll worry about it later. But we also have the angular part, right? Remember we have 3 dimensions. We have to have 3 variables for our coordinates. We have r and our 2 angles, theta and phi. And this is what I call the angular part, and that's what we're going to focus on pretty much for the next couple of lectures, because it's really not only the most important part of the atom, as we'll see. I don't know if that's true or not. I want to say that it's the most important part, but I might be a little biased. But it's essential, and the physics that we're going to learn about angular momentum, the physics and the energy of something orbiting, something rotating, is something that's applicable to not just the hydrogen atom, but to basically everything. It's in some ways the most important most important model for physics or chemistry, quantum mechanics, next to the harmonic oscillator. Because what do molecules do? They move in space through a box, translate, they rotate, they vibrate. Right? So we're going to talk about rotation here. Angular momentum is just as important as vibration. And what we'll see is that it's a universal theory. Angular momentum is completely universal. It doesn't really matter what the object is. You can rotate it. If it spins in an oscillatory fashion, the theory applies to it. And once we get through all of this, we'll come back to that idea of color and flavor for the electron. These are renamed properties that I gave you in problem set 1 for spin. The spin of the electron. And spin is an intrinsic angular momentum of the electron. All right. So once we learn about how things rotate, we'll be able to talk about how an electron has spin. And we'll be able to derive the theory for it very, very quickly. Very, very simple. Spin is surprisingly straightforward once you understand how things rotate. So once we have all that, we'll understand everything we know about the angular part of the hydrogen atom or any angular system. And then we can tackle the radial part and then put it all together to get a hydrogen atom model. So, but we got to grind through this a little bit. And this topic is very near and dear to me because my PhD work, my research, not just my PhD work, but my research today, involves angular momentum. I study the rotations of molecules and the spectroscopy of rotations of molecules, which is unfortunately not something I can really emphasize right now. I would like to talk about it because it's near and dear to me. I've spent 15 years doing this. Well, not quite 15, maybe like 12 years now, I think about 12 years doing this. If we get some time near the end of the class when we talk about spectroscopy, I'll try to focus on it just to give you some insight about my little weird world of spectroscopy. But the theory here is directly applicable. All right, so we haven't quite got to quantum mechanics yet. We've only been talking about things rotating classically. Right? So here's my magical rotator. Right, the idea is we have two objects with masses m1 and m2, and we fix the distance between them. Right, we're fixing r. Right, r is fixed, and we give this a name. Fixed r, or rather, something that rotates with a fixed distance, is what we call a rigid rotor. Okay, and again, you can think of this as a harmonic oscillator if you want. You bought two things attached by a spring that you're spinning. Right? And the idea is that when you spin it, it doesn't stretch. Right? Now, if you've ever spun a slinky before over your head like this, you know it stretches. When you rotate it, you have that centrifugal force pushing away from the center of rotation. Right? That stretches the spring as you rotate it faster and faster. Right? But a slinky is not a rigid rotor. You have what they call the Coriolis effect, which couples vibration, the motion of stretching, to rotation. Right? You rotate and the thing stretches. Right? Intro physics calls this the centrifugal force, which isn't a real force. But this coupling of rotation to vibration is called the Coriolis effect. It's the reason why when you flush the toilet in the northern hemisphere, your water goes clockwise, and in Australia it goes counterclockwise, because the coupling of the angular momentum of the Earth couples in the opposite direction on the southern hemisphere as the north hems. Okay, so we're rotating this object in space, and the important thing is that we're rotating it about its center of mass. Okay, so the system is rotating around this fixed point, which you can measure as for instance, the center of mass is the origin of our coordinate system. Right, and we'll talk about angular momentum more carefully today, but let's talk about the very simple parts of it, which is that angular momentum is a vector, L. Right, this is what we call angular momentum. There are other labels that we use for it, but L is the most common term we use for angular momentum. And I don't want to talk about the vector properties of it yet. I want to just talk about the magnitude. Right? Remember, we think about momentum. Momentum is a vector. It has a direction, right? But we want to think about the magnitude of the angular momentum here. How fast is it spinning? And I wrote this equation down last time. It's equal to I, the moment of inertia, times the angular frequency. So this is what's called the moment of inertia. Sorry, this is moment. And it has units of approximately kilograms times meters squared. And we have what we call our angular frequency, which has units of radians per second. All right, radians aren't a real unit, but I like to write it there to be consistent. The idea is that the moment of inertia is an effective mass of the system, the rotational mass of the system. For a two-body system, the moment of inertia, so for this barbell, I is equal to the reduced mass of the system, just like the harmonic oscillator, times the distance squared. Okay? Every object has a moment of inertia. You can calculate it. completely general idea. But for a barbell, it has a really simple formula. It's the reduced mass times the distance between the masses squared. A really easy equation. And angular frequency is literally that. How fast is the system oscillating in time? In other words, how many, if a full rotation is 2 pi radians, right, if it rotates 360 degrees, that means it's gone 2 pi radians. Angular frequency tells you how many radians does it move per second. Okay, so if just as an example, if the period is 1 revolution per second, all right, so it goes through 2 pi per second, then omega is 2 pi radians, or 2 pi per second, right? It goes through 2 pi radians per second. All right? You might think of this as a frequency, and it is a frequency, but a frequency, like when you think of things in hertz and megahertz, when you think of energies, like E equals h nu, Planck's law, that frequency, that's how fast the system, how many times it goes around the circle per second. All right, so we also have this other frequency that we often talk about, V.
Is that supposed to be 1 pi, or is that...
2 pi.
No,
I'm sorry.
1 revolution?
1 revolution per second, yes. Right, so if omega is 2 pi seconds, the frequency of the system is omega over 2 pi, which is 1 hertz, 1 per second, right? So sometimes you'll see these two terms, omega and nu, V. I always give it a little squiggly V. Right? V is, like in Planck's law, E equals hv. That's how many revolutions the system goes per second. Whereas omega is the number of radians, right? How much of a circle per second it moves around. Okay, so they're just off by a factor of 2 pi. Okay, so I could easily convert omega into V and just write 2 pi V instead of omega, and we'd be fine. We could use the same, we use hertz and everything. Right, so it's just a factor of 2 pi that we're dealing with here. But again, all this is saying is that momentum is equal to mass times velocity. That's what this means. Instead of a velocity, we're not moving in space, we're just rotating. So this is an effective velocity of our system, right? How fast the masses are moving around a circle, and this tells you the mass, right? Remember, momentum, linear momentum, the magnitude of it is m times v, right? Just like I times omega. Right, so everything is exact. The math is very similar, except everything's a little funky because it's going in circles instead of going through space. Right? The circle is stationary, centered at the center of mass. Things not moving in space, it's just rotating. All the physics work out the same. Okay, and a really nice formula, right? Ultimately, we want to do quantum mechanics on this, right? We want to think about the quantum mechanics of a microscopic rotor. And so we want to relate this. Remember, when we do quantum mechanics, we need to solve the Schrodinger equation, which means we need to understand what the energy of this angular minimum is. Right? We need to know the energy. And that formula is really, really easy to solve for. And we just go to general physics to get it. But that the kinetic energy of rotation, so T for rotation, so we'll say angular, the angular kinetic energy, this is kinetic, is L squared, the magnitude squared of angular momentum, divided by 2 times the moment of inertia. Okay, and I just want to convince you that this is kinetic energy. I did this last class, I'm just doing it one more time. If we plug in our value for L, IW, we get I squared W squared in the numerator, divided by 2I, which is just 1/2 I omega squared. Right? If I, again, unfunk myself away from circles and move the linear motion, right, this kind of looks like 1/2 mv squared, right? Just like kinetic energy. Okay, so nothing's really different. We've just made everything go in a circle instead. But the math all works out the same. All right, we just have funky numbers now. We have angular frequencies and we have effective masses, inertial masses of rotation. Right? And the best way to think of moment of inertia is remember that when you rotate, and this is the example that we give as rotational spectroscopists to undergrads and stuff all the time, is that if I take a figure skater, let's say Dr. Luzik, who actually is a figure skater, and I exert a fixed amount of force on him to spin him. Okay? So let's say I put in a fixed amount of energy in, right? I give him some torque and I push him with a fixed amount to get him to spin. And Dr. Luzik's got his arms closed like this, right? And so what's his moment of inertia? Well, he's got some mass. I don't know how Eddie weighs, but we'll just say he's got some mass. And R here will be, of course, the length of his body, right? So when his arms are closed, his moment of inertia is small, right? Because R is small. The extent of his body is very short. Right, so I give him a fixed amount of angular momentum. I give him a fixed amount of energy, and his I is small, which is going to mean his omega is large, right? So when a figure skater's got their arms closed like this at some fixed rotation speed, or some fixed energy, they rotate very quickly. But what happens to a figure skater when they open their arms, right? When does Dr. Luzik open his arms like this and start spinning? Well, his I increases. Right, so he's got a fixed amount of energy, but his I is getting bigger, which means omega gets smaller, right? He starts to spin more slowly. Right, so this inertial mass works exactly the same way as a normal mass does in linear motion. Right, but instead it's dependent on what is the size as well as the mass of the system. Okay, and molecules and everything work exactly the same way. Fixed amount of energy. You put a fixed amount of energy into rotating a molecule. The bigger the molecule is, the slower it rotates. Slower its frequency.
And would it slow down at the rate of whatever the value is squared?
Correct.
Okay.
Yeah, it goes square root. That's correct. Yes, you're precisely correct. Okay. So this is a nice equation, right? This gives us a reference, right? If we can come up with some way to express angular momentum in terms of quantum mechanical operators, we can write down the kinetic energy and solve the Schrödinger equation for it. But it gets one better. We don't even have to do that because we know the form of the kinetic energy of any system. Right, we write it down every time we write down a Hamiltonian. It's minus h bar squared over 2 times the mass times the second derivative with respect to position. So we know that L, the operator for L, right, the thing that we actually use to measure angular momentum for a quantum mechanical system, has something to do with the kinetic energy. So let's go ahead and think about this problem and see if we can come up with a kinetic energy relationship for our quantum mechanical rotor. Okay, so let's work out this math a little bit. So let's move now to the proton-electron system. All right, so don't think molecule, let's think proton and electron. Just like our atom, our hydrogen atom. All right, and they're at some distance r. Okay, and so the moment of inertia of this system is mu r squared. What is mu? Well, mu is the mass of the electron times the mass of the proton divided by the sum of the masses. By the way, on problem set 3, I saw some people write this the other way around. Thankfully for HCl, the reduced mass is about 1 AMU, so the inverse is about 1 AMU, so you weren't too far off. But just remember it's product over sum. Times r squared. Okay, and remember the proton, but remember that the mass of the proton over the mass of the electron is about 1,000. Okay, so that means that the mass of the proton, the mass of the electron is basically negligible. Right, so I could write this as a little me times a big MP to indicate the size, with a little me plus a giant MP in the denominator, times r squared. And because MP is much larger than ME, we can neglect the ME in the denominator. It doesn't really add much, right? It only adds 1 1,000th of a percent, or 1/1000th. So we can cancel that out, right? And we're left with ME MP over MP times r squared, right? And we can cancel out the MPs. So the moment of inertia of our atomic system, our hydrogen system, is just dependent on the mass of the electron, right? This is the Born-Oppenheimer approximation, that the nucleus is just a giant lumbering elephant, and the electron is just buzzing around it. The proton isn't affected at all by the electron. The proton just sits there as if nothing happens. So all of the angular component, all the momentum, is derived solely on the motion of the electron up to this limit. Okay, so we have now that the kinetic energy, which I'll write as an operator, is going to be equal to the operator for L, which we don't know yet, divided by 2 times the moment of inertia for the system. Well, that's just 2 MER squared. Okay, but what's the kinetic energy operator for any particle from the Hamiltonian? Well, it's going to be minus h bar squared over 2 times the mass of the electron times the second derivatives with respect to position. Right? It relates to the motion of the electron in Cartesian space, just like before. Right? So if you look here, we have some nice relationships here, right? We can cancel out the 2me on both sides, and we're left with that the operator for L squared is minus h bar squared r squared times the second derivatives. Now, there's a problem. What's the problem? Well, we have an issue with our variables. We have r here, and then we have this thing that's proportional to x, y, and z's derivatives. All right, so we've come back to that same problem that we had the first class when we tried to write everything down in terms of Cartesian coordinates, x, y, z. We realized that we had to move the spherical coordinates because we have this r problem. This coordinate is dependent on all three directions simultaneously, right? X squared plus y squared plus z squared. And this is and the kinetic energy is independent, right? It's only dependent on one direction at a time. So we have something that's coupled, all 3 coordinates is coupled, and then we have an uncoupled derivative here, differential operator. So we have to, this is just begging us to go back into a new coordinate system. So we have 2 options. One, we could write r squared as x squared plus y squared plus z squared, or we can convert this part into spherical coordinates. And that's what we're going to do. That ends up being the easiest way to tackle this problem. Right, if I write this as x squared plus y squared plus z squared, that math is miserable. You can do it, but it just begs you. It just begs you to switch to spherical coordinates. And that's what we want to. That's what we ultimately want to do anyway, because remember, this is an angular problem. We're rotating something around a circle. So using x, y, and z is not a really useful way to do it. We need to express things in terms of our angles. Right? And we know r is fixed, so if we have any derivatives with respect to r, they're going to go away because r is not changing. We know that once we put all of this together, the derivatives are only going to be dependent on the 2 angles, which is what we really want. We want to know how the angular momentum depends on how the angle of the electron changes as a function of time, or how the energy changes as a function of angle. So what we're going to do is we're going to take this thing right here, this operator. We have a name for this operator that I don't typically use, but if you read the textbook and follow it, it's what the textbook uses. This is what it's traditionally called, the Laplacian. And the operator that we often use for it, the notation for it, and I'm just going to write this down because it's useful in case you see it, is an upside down triangle with a square to it, del squared, the Laplacian. All right, it's the second derivative operator. All right, the reason why it's called the Laplacian is after a famous French mathematician named Laplace, who actually was as we'll see in a second, he's the one who first solved this equation. Not for quantum mechanics, but for regular rotations, and I'll tell you where Laplace's involvement comes in and why it's related to this problem. He wasn't concerned about angular momenta of molecules. He was concerned about waves, electrical fields, and electric waves. And this del operator comes into the equations for waves and electric fields. So he names it after himself. Or he doesn't name it after himself, someone else names it after him. Okay, so we have to convert the Laplacian into spherical coordinates. And let me tell you, so it's doable, it's algebra, it's chain rule, and it's going to give you it gives you this ungodly, ugly equation. All right, so what we're going to do is actually make this look more complicated. But we're going to be able to make some simplifications. And it will actually allow us to massage the equation into something we can solve. But you're just going to have to bear with me a little bit, because it's pretty ugly. All right, so when you take all of those, I think it was like a lecture or two ago, I talked about spherical coordinates. So when you replace x with the spherical coordinate version of x and y and z and so on, and start taking all these derivatives to convert it to r, theta, and phi, you get this rather complicated expression. So when we take del squared and we move to spherical coordinates, r, theta, and phi, we get three terms, just like we do before. There's still three terms, one for each value. And I'll break it down into each of these three terms. First is the term dependent on r. Okay, so let's look at this equation a little bit. So what this is saying is that the r part of this is the derivative. So I would plug in the wave function here. If I were to apply the wave function here, the wave function would go in here. So this operator takes the derivative of the wave function with respect to the radius, multiplies it by r squared, takes the derivative again, and divides it by r squared. Okay, so if you blur your eyes enough, we've got some chain rule and some product rule problems here, but ignoring those, if we just did kind of a really sloppy rearrangement of these terms, it kind of looks like r squared times 1 over r squared times the second derivative with respect to r. Right? So this operator really just kind of looks like one of these terms. Right? There's just this extra r squared that eventually gets canceled out later on. Right? That's not really how it works, because there's the product rule here. Right? When you take the derivative of this inside, you got to take the derivative of this times this plus the derivative of this times this. Right? So it's a little different. But you can see that it kind of looks like a second derivative with respect to radius. It's just got some extra terms in it. So this is our radial derivative. That's the radial term. And then we're going to have terms for theta and phi as well. So I'm just going to put a big box here so you know where they are at. The next term is 1 over r squared sine theta times the derivative with respect to theta times sine theta d theta, d by d theta. All right, again, scary looking term. But again, it doesn't look all that much different. Right, here's the second derivative with respect to theta. The signs will eventually cancel out, and there's this extra 1 over r squared that comes from the conversion between x, y, and z and r, theta, and phi. There's always this extra r squared. So that's what that is. Okay, so this is our theta term. This is our theta angular term. And then we have the phi term. So I'll add a plus here for the last term. And the last term is 1 over r squared sine squared theta. Let me make that theta a little bigger. Sine squared theta times the second derivative with respect to phi. So this is our phi angular.
What does
term.
it say? Plus theta angular momentum?
No, theta angular term. It's the theta angular term. So the plus here. Let me just erase this. Let me make this more consistent. All right, there's a plus here, and this is the theta angular term. Okay, and this is the phi angular term, and this is. Let me just erase this here, just to make it a little more organized. This is the radial. Okay, so this is our new differential operator in the kinetic energy. It's ugly, and I'm never going to make you do anything with it. I just want to write it down and talk about it. All right, so you don't actually. Most people don't ever go back and actually. The point where you actually do this by hand and solve it is until graduate school usually. So we usually introduce it to talk about it because there's some things we can learn. But we're not going to solve it explicitly. We can just appeal to the solutions that the textbook or any other physicist will give us. And if you want to take quantum mechanics in graduate school, you'll have to come back and solve this problem on your own. It's not too bad, but it's a lot of variables. It's a lot of algebra. All right, but the important thing is that, again, nothing's really changed too much. We've just kind of fudged our coordinate system, and we've added some complications. Right? These terms look scary, but instead of going initially in Cartesian system, we have a term that is uncoupled in the position times a term that's coupled in the position. Right? R is square root of x squared plus y squared plus z squared. And now we've gone into three terms. We've converted into three terms that are independent of each other. Right? This term is only dependent on the change in r. It's only dependent on change in theta. So it's only dependent on the change in phi. Right? And then we're going to take this and multiply it by minus h bar squared r squared. Right? And r is uncoupled. Right? R is one of our uncoupled variables. So we've gone from a coupled solution, a coupled differential operator, where it depends on all values simultaneously, to one that depends on where you have a sum of three terms that are all independent of each other. Right? The change in r is not dependent on the change in theta or the change in phi, and so on and so forth. They're all uncoupled from each other. So we have actually simplified the problem, even though the equation itself looks worse. All right, so let's go ahead now and write down our L squared operator. Put this all together. Which is minus h bar squared r squared del squared. This is that's a hat. Okay, and the important thing to note is that this radial term, remember in our problem we've assumed a rigid rotor, that r is unchanging, right? We only care about the angular part right now. We don't care about r. R is fixed, rigid rotor. This term is 0 for a rigid rotor, right? Because there's no change with respect to r. The system doesn't move r. R is a fixed number. So this term right here is completely 0. It goes away. All right, so we don't have to worry about the derivative with respect to r for the rigid rotor. And so when we calculate our operator for L squared, we're going to multiply del by r squared. This r factor disappears completely. Right? There's no dependence on r in L squared anymore. It's all gone. Right, so this ends up being minus h bar squared times 1 over sine theta d by d theta of sine theta d theta plus 1 over sine squared theta times the second derivative with respect to phi. because we've assumed all this, right, we've reduced our problem to something that's only dependent on the two angles. Exactly what we want, right? We want to reduce this to an angular problem. And that's exactly what we did. We've removed all, right? Angular minimum has no dependence on r. There's no r in the equation. It's completely fixed. Right? L is completely independent of r. Precisely what we want. All right, so what we need to do now, right, we have an operator here for angular momentum squared, the magnitude of the angular momentum. So when we apply this to a valid wave function for our system, we should get a number back times the wave function, right? The eigenvalue equation. Right? We want to take this equation and find the wave functions such that when we apply L squared to them, we get some number. I don't know what the number is, but we'll calculate it, times psi. Sorry, that's not supposed to be a circle. Right, so we need to come up with some wave functions that when we apply this operator to them, we get the wave function back. All right, we're not going to solve this in this class. But that's okay, because Laplace solved it for us 250 years ago. He was looking at something different, though. So what I'm going to do is I'm going to write down the results of this. All right. So I'm going to write down what the results of the wave functions are, what the wave functions are, and what the eigenvalues are. What are the allowed values for angular momentum? All right. So we'll just basically I'll just solve the equation for you. We won't worry about the solution so much, and then I'm going to try to show you where this result actually shows up classically. Why Laplace solved it in the 1700s, early 1800s, when he didn't know anything about hydrogen. He didn't care about hydrogen. He was worried about waves. And this equation shows up in wave propagation. And I'm going to show you exactly, or I'm going to talk exactly about where the classical analog of this is. Okay, so we're going to solve this equation. And what we find is amazing. Really, really simple result. That L squared applied to it, the wave functions, is equal to h bar squared times this new quantum number, j, times j plus 1. Sometimes it's called L. Sometimes it's called j. I'm going to use j for now because it'll be useful to use the letter j. Or you could also write sometimes L instead of j. When we talk about the hydrogen atom, I will tell you the difference between why we use j and L. It's not important right now, it's just a label. And j here is what's called the total angular momentum quantum number, right? It's our index for angular momentum, right? Remember, every quantum mechanical system is quantized. It has a quantum number associated with the allowed states. And j can be any number, any integer, between 0 and infinity. Okay. So it's just like the harmonic oscillator. Right? Harmonic oscillator knew the quantum number v can be any number between any integer from 0 and up. But we have a slightly different expression. So remember, the harmonic oscillator is v plus 1/2. Here it's j times j plus 1, or j squared plus j, however you want to think about it. Okay, so it has a slightly different structure, but again, it's just a very simple formula. Right, so what does this say? Right, so we need to think about how to interpret this equation a little bit, and I'll get to that. But I want to first show you what the wave functions of this system are. What are the allowed, what is the, if you will, what is the probability distribution of where our electron will be as a function of angle for each of these angular minimum states? And so the wave functions for this system, we have another label for. So the angular wave functions of our system, which are functions of theta and phi, right? There's no r dependence on them, have a very special name and are a very special set of functions that have been known for many years. I mean, Laplace was the one who came up with them 200 years ago. All right, and we have a very special label for them. We give them the label Y, and they take two numbers, J and M. And they're functions of theta and phi. All right, so they have two labels, M and J. By the end of this class, we'll understand what both of them are. J is the same as this one, by the way. It's the same J. So this wave function is dependent on J, but it's also dependent on this M number that we haven't defined yet, but we will. All right, and these have a very special name. They're well-known functions. They're called spherical harmonics. The spherical harmonics. Okay? They're a special class of functions that are effectively the solutions for rotation, for angular momentum, for waves, for systems that are like waves contained on a spherical surface. Remember, the hydrogen atom is spherically symmetric, right? So you can imagine this hydrogen at a fixed R can be somewhere on this sphere around the proton. Right? And the spherical harmonics tell you, as a function of these two numbers, whether the angular momentum is 0, 1, 2, 3, or whatever, and we'll talk about M in a second. This tells you, basically, when you take the square of this, where on the sphere would you find that electron? Okay, so these tell you something about the average kind of space where the electron exists on this fixed radius sphere around the proton. Right, so they don't tell you anything about the distance. We still have to calculate how does the probability the electron vary as a function of the distance from the proton. But this will tell you as a function of angle for fixed distance where on this atomic sphere, if you will, the electron exists as it rotates. The reason why this equation has been known for a long time is that if you take a ball, a sphere, and you apply an electric field on it, all right, so you have a sphere that has a charge potential to it, okay? So if you apply a voltage to two leads on a sphere, and so the sphere has an electric field, there's electrons and waves oscillating around the surface of this sphere. Right? A great example of this is the Van der Graaf generator, which are those giant glass balls that they have at science museums, and you touch your fingers to them, and the little lightning sparks come up to your fingers. Right? Think like that, but now the entire surface of the sphere has an electric field. Well, it's just like a Van der Graaf generator. And the solutions for this system, basically, what's the shape of the electric field on the surface of the sphere can be represented as the spherical harmonics. Okay, so there are different types of stable solutions for an electric field on the surface of a sphere, and each one of those stable surfaces or trajectories or fields or whatever you want to think of them as are represented by a spherical harmonic. Okay, so the idea is that waves propagate harmonically in a classical electrical field on a spherical surface, just like how an electron exists on this sphere as a particle. It's also a wave. Right? So the wave solution of electric fields on the surface of a sphere is just like an electron's wave-like behavior on the surface of a sphere as well. Okay? There's a reason why that is, right? Electric fields are dominated by interactions between electrons. So not surprisingly, when you put the electromagnetic interaction between these electrons on a sphere classically, you get things that look like the behavior of an electron on a sphere by itself. And of course, Laplace and Maxwell and all these guys that did electric fields, they didn't have any idea about this. It wasn't until the 1920s that when they went to solve this hydrogen atom that they realized that the same thing applies to the electron on the hydrogen atom. That the spherical harmonics for the electric fields on a sphere are the exact same solutions as the electron. Really, really powerful connection there. Not surprising that electrons which generate electric fields have the same behavior as electric fields. What I want to do is, before I write down functions for these, because they're just functions, I want to draw some for you. And when I draw them, you're going to look at them and be like, well, geez, I've seen these before. You've known about spherical harmonics your entire chemistry career and you didn't even know it. And then it'll start to make sense why we're talking about the hydrogen atom and why this is relevant. I just got to get my pretty picture. Here we go. Okay, so before I talk about the physical nature of this extra number, m, right, I'm just going to show you how m is related to j. They're related to each other. And then we'll come back and I'll define m at the end of the class. And we'll talk about it next class. We'll talk about m point. Trust me, it'll come back. So if j can be any integer greater than or equal to 0, then it turns out that m can be any value between minus j and plus j. Okay, so what does that mean? So let's think about that for a second. If j is equal to 0, then the only allowed value of m is 0, right? Because it only runs from minus 0 to 0, so it's 0. Okay, and so the wave function for this system is the 0, 0 spherical harmonic. Okay, I won't write down the functional form of it just yet, because I want to plot it for you. Let me do a, I don't like this. I need a full plot. So just to make things easy, I'm going to convert back to x, y, and z, because we always think in terms of Cartesian coordinates. Easier to visualize things in Cartesian coordinates. And if you plot this function, and I'm going to plot the square of it because we've measured the square of the wave function. And a spherical harmonic is just a circle on the YZ plane. It's just a circle. All right, this is a two-dimensional cut. Sorry, it's a two-dimension on the YZ plane. So it's spherically symmetric across all, so it's actually a sphere. It's a sphere. Okay, so the lowest energy state of angular momentum, the wave function just looks like a sphere. What does that mean? That means that the electron has equal probability to be anywhere around the proton. Spherically symmetric, a perfect sphere. So the electron can be anywhere. It's completely independent of position, of angle. Right, so the formula for this function which is normalized is 1 over 4 pi. There is no angular dependence. It's just a number, right? A sphere has no angular dependence. It's the same, looks the same in all directions. So the wave function for rotation in the ground state, j equals 0, no angular momentum, is just a sphere. It means the electron can exist anywhere. All right, so what about j equals 1? Let's go up a j, right? Let's give it 1 unit of angular momentum. Let's start spinning our electron around the proton. Let me make some more space for this, sorry. Well, if j is equal to 1, then m can be 3 different values, right? Because m runs from -1 to 1. So it can be -1, 0, or +1. Which means there are 3 different states with angular momentum +1. 1 unit of angular momentum. All right, remember, everything's quantized, right? So you can only spin up, your system can have 1 quantized unit of angular momentum, it can have 2, it can have 3, it can have 4, and that's it. Right? It can't have anything in between. But there are 3 possible solutions, 3 possible different states, substates, if you will, that all have j equals 1. Let me draw them for you, and then you're going to start realizing what these are. because it's not obvious from the sphere, but it will become obvious with these. So we'll draw the +1, the 0, and the -1 like this. Let me give myself a little. That's probably enough space. No, I'm sorry, guys. I don't have enough space to plot this, so let me just plot them one at a time. Okay, so I'm going to make 3 plots, one for each. Right, and this will be the m equals +1, the 0, and the -1. And let me make sure I get my axes right. This is going to be z and x. This one's going to be y and x. And this one's going to be x. Sorry, no it's not. This one's going to be y and z. There we go. Okay, 3 different combinations. I'll start with the 0, 1. That's not what it should look like. Sorry, it's making it into a circle, which I don't want. It has this lobe-like appearance. And of course, these are also cylindrical. They have cylindrical symmetry. So they're 3-dimensional. They're lobed like this. The 1, 1, so the +1 looks like same thing, but it's along the y-axis instead. Sorry, I'm having problems with my pen. There we go. And the -1 is along the x-axis. Symmetry axis. Right. So these are what the 3 spherical harmonics. These are the chi-squareds for them, right? This is the square of y -1, 1, and so on and so forth. What do these look like to you? Where have you seen these before? Say it again, a little louder, please.
Orbitals?
Orbitals. What orbital is this? In hydrogen. What does it look like? Which orbital? What?
S.
S. And what do the other ones look like? Yeah, how many P's are there?
3.
Yeah, there's 3. Not a coincidence. The shape of the atomic orbitals, the P lobes, the S lobes, the D lobes, the F lobes, whatever you want to call them, they are products of the angular dependence of the electron. The shape of the orbitals arises exclusively from angular momentum. Now that seems odd. But and then you go back to that idea of those classical fields that I talked about on a sphere. How do you have an electric field that looks like these lobes? You do on a sphere. You can create spheres that have these stable solutions that look like this, where the electric field is only exists on kind of a cylindrical cut of the sphere, instead of it being spherically symmetric. Right? These are completely general. Right? So we often call these spherically symmetric ones, where m is equal to 0 or j is equal to 0. These are called S waves, like S orbitals, and these are called P waves. Okay, you see this kind of behavior, this lobe-like behavior, the spherically symmetric behavior, S and P behavior, D behavior, whatever you want to call it, in everything. Anything that has angular momentum that's microscopic has wave functions that have this angular dependence. Sometimes you can even watch when 2 molecules collide. Depending on how they collide, they get sent off in some direction, and depending on their angular momentum, if the net angular momentum of this collision is 0, then the resultant molecule will get scattered off and fly in a symmetrically dependent way, or independent way, spherically independent way, right? The thing that flies off at angular momentum goes in all directions. If the angular momentum of the collision complex is 0, they're not rotating together. The molecule will just fly off in any direction. But you can get if you can get the system to collide in such a way that it also has angular momentum, the resultant molecule or the resultant product that bounces off and scatters off the reactant complex will fly off in one of these 3 ways. It won't go off in a spherically symmetric way. It'll go off in a cylindrically symmetric way. So if you have two objects that are rotating like this, and they collide and they scatter off and conserve that angular momentum, the thing that flies off of it will either fly in a cylindrically symmetric way along the y-axis, the z-axis, or the x-axis, like a p-wave. Right? You can get angular distributions of your reactions in the gas phase with S-wave character or p-wave character. And they see these kinds of things in high-energy physics as well. You see S-wave scattering and p-wave scattering from when a system collides together and has some net angular momentum that's conserved. If that angular momentum is conserved, then your distributions, your angular distributions, your products will look like S and P orbitals. Right? Completely universal. People use this kind of idea, this idea of creating electric fields that have this lobe-like behavior is the basis of quadrupole trapping, ion traps and magnetic and mass spectrometers, right? How do we trap ions in a unique way? How do we get them to size select and to separate them as efficiently as possible to do mass spec? We create magnetic fields and electric fields that have these kinds of asymmetric or cylindrically symmetric behavior. We can focus things and make sure they're moving in a certain direction, right? Because if you have an electric field that you want to trap or slow down ions that's spherically symmetric, the ions are just going to fly off in any direction. But you want to focus them in towards down an axis, right? You want them to all kind of separate slowly, and you want them all to go in the same direction, right? So you want to build an electric field that looks like this, so that when the molecules come in, they get focused in by the electric field and move along that z-axis instead of moving off in all the different axes. Okay, so you can do this in electromagnetism. Atoms show it, molecules show it, everything. Anything with electric angular momentum, anything that can have angular momentum, have behaviors that look like this. Okay, so it was really surprising and a big deal when they discovered this, because they understood these things about electric fields. You can make spherically symmetric fields. You can have these lobe-like fields. And to see that the hydrogen atom also shows that same behavior is a really good sign. Okay, so I won't talk too much about what the functional forms of these harmonic oscillators or these spherical harmonics are just yet. It's not super important at the moment. Just to know that you already have a sense of what they look like. You know what the S and the P's and the D's look like. And in general, right, if J is equal to 0, these are S, J is equal to 1, and there's one orbital, right? There's one S orbital. J equals 1, that's P. There's 3 of them. J equals 2 is D. There's 5 of them. J equals 3 is F. There's, it's 2n plus 1. 7, sorry. 7 of them, right? All those numbers that you learn from general chemistry, they all come from angular momentum. You know the rules. You know all these different little angular momentum rules, and you just never do it. But the way that the orbitals arrange in atoms is completely dependent on their angular momentum. The electron's angular momentum.
Is that supposed to be D for 2? J equals 2?
Yeah. Yeah, D. Okay, so we've already... Right, so this is why we split the hydrogen atom into 2 parts, a radio and angular part. By solving the angular part, we solved half the hydrogen problem. We got the S, we got the P, we got the D, we got the F. But we didn't get the 1S, 2S, 3S, 4S, 5S, 2P, 3P. We didn't get the numbers. The principal quantum number, the N, that comes from the radial part. Right, so we've gotten the orbital structure, the angular momentum structure, which is the PDF, but we haven't gotten the N part yet. Right? 1S, 2S, 3S. There are as many S's as you would like. There's not just one, there's many. And that comes from the radial part. That comes from the size of the orbit of the electron, how far the electron is away from the atom for the proton. Right? That will determine N. So that's why we're halfway there. Right? So the radial part will give us N, and the angular part gives us the P and the S and the D and so on and so forth. I'll just write that down so for hydrogen, each orbital has 4 quantum numbers, N, L, M sub L, and M sub S. We haven't gotten N yet. N is the radial. The L quantum number is L squared, angular minimum. We could just write that J. It's J, effectively. This M sub L is M, which we haven't talked about yet. This is angular. And M sub S is spin, which we haven't talked about yet either. Okay? But the point is that we've by solving for the angular part, we've gotten more or less half the hydrogen atom done. Right, we've gotten the L, and we haven't talked about what M is yet, but we have those 2 quantum numbers. They're the indexes of the spherical harmonics, and we saw that there are 2 J plus 1 M states. Right? So what does this mean? This tells you again 1s, 2s, 3s. This tells you whether you're S, P, D, or F, and M tells you which P or D orbital you're in. You're in the X, you're in the Y, you're in the Z. Okay, I'm going to show you what that means in terms of angular minimum. We might not have time for it today. Maybe next class. Come back to it. Okay, so this is what we ultimately want to get. We want to come up with a model that's got 4 numbers, 4 indices. So we've already gotten 2 of them, L and M sub L. Let me just show you very briefly. Actually, I have enough time for it. Where M comes from, and then we'll go back next class on Tuesday and start thinking about things a little more quantitatively. Okay, so what I'm going to do to explain how does J and M are related, all right, we're going to appeal to vectors. We're going to look at angular momentum as a vector. And most people sit and cry when I do this, but the math's not too bad. Everyone loves vectors.
Is everyone in the room with us?
No, everyone but you guys probably. So the vector model. All right, we'll actually appeal to this quite a bit because it's a really nice way to visualize things, and it actually helps us a little bit. All right, so what I'm going to do is create a little coordinate system. It doesn't really matter what the axis is. We'll just say this is X and this is Z. It doesn't matter so much. And what we're going to do is we're going to shift our coordinate system so that our vectors, our momentum vectors, our position vectors and stuff all originate from the origin, right? So the proton is here. And there's a position vector, R, which points to the electron, like that, right? With some angular vector, some position vector. It's pointing to the electron, and what we're going to do is we're going to apply a momentum, a force, to that electron and give it some momentum in some direction. Right? So I'm going to, let's just say, apply sorry, let me do a slightly different angle. Apply momentum to the electron P in this direction. Okay, so I've got the electron on a leash at fixed R. And I'm going to push that electron with some momentum, linear momentum in some direction. Right? The resultant angular momentum, remember P is just M times the velocity vector, just as a reminder. L, the resultant angular momentum vector, is the cross product of the momentum times the position. Okay, so in order to figure out which way L is pointing, we have to use the right-hand rule. Right? So if R is here and E and P is here, my middle finger is R and my index finger is P, then the cross product of them two will be out of the plane with my right-hand rule. So angular minimum is going to be pointing out of the plane in this direction. So angular minimum is perpendicular to the plane that is drawn out by P and R. If I were to, I'm just going to kind of sketch this a little bit. Right, we've got this plane here between P and R. And angular momentum, I'll do it in purple, is out of the board. I can't really draw it. Perpendicular to the two vectors. Right? So if R and P are like this, L is sticking out. Not a very good drawing, but sticking out of the plane. Like this. Okay, so what I'm going to do now, well, now we know which way L is pointing. What I'm going to do now is I'm going to shift my coordinate system again so that L originates from the origin. All right, so I'm gonna just shift all my vectors so L is now at the origin instead. I'm just shifting my coordinates a little bit so that now my coordinate system has my electron right here in the center, and it has some, oh, so it's perpendicular, so that's going to be the y-z plane, sorry. And angular momentum is pointing in some direction here. All right, so angular momentum is pointing along this direction. I'm just rescaling my vectors a little bit because it's always easier to work with vectors that originate at the origin. And so we have a couple questions to ask, right? What's the length of L? What are the things we have to ask about a vector? What's the direction and what's the length? All right, so we know that L squared, the square of the length, the magnitude, is h bar squared j plus 1. Right? That's what we calculated. Right? That's the operator. It says that the angular minimum is a function of j, and it's h bar squared j plus 1. So that means that the length of the vector is the square root of that. It's h bar squared j plus 1. Right? And that means, of course, L can only be certain lengths. Right? It can be 0 h bar. It can be, what is, if j is 1, that's 1 times 2. That's the square root of 2 h bar. If j is 2, 2 times 3 is 6. That's the square root of 6 h bar. Right? And so on. Right? These are the fixed lengths, the fixed angular minimum our system is allowed to have. So the length of this vector is h bar square root j plus 1. Okay, so we know how long the vector is, but what's its direction? Right, what are the components of it? Well, I'm going to spoil the answer for you. And then next class we'll actually derive the answer, why this is true. In quantum mechanics, you can only know, well, remember, so it's a three-dimensional vector, so there's three components, right? The vector L. So if we're in the right direction, we write L as Lx times x hat plus Ly times y hat plus Lz times z hat. Right? We have a little vector that's pointing in the x, y, z direction, some direction with three components. In quantum mechanics, if we measure the length of L, all right, so if our system is defined based on the magnitude, right? That's how we solved our Schrodinger equation, is we found wave functions with constant length, or constant magnitude of angular minimum. The angular minimum is fixed. When you fix the angular momentum for each of your wave functions, you can only know one direction at a time. I can't know Lx, Ly, and Lz. I can only know one of them. So either I know L squared and Lz, or L squared and Lx, or L squared and Ly, I can pick one of those pairs, and that's my only option. So I can only know its direction along one of the axes. It's even worse than that. If I somehow set my wave functions so that I know, say, Lx, right? I solve for the wave functions that satisfy Lx. I still can't know Ly or Lz. The only thing else I can determine is the length. So I'm always fixed to either with having the magnitude in one direction only. No matter what I do, I can't cheat and get two directions out. This is, as we'll see next class, this reason that I can't know Lx and Ly together simultaneously is precisely the same reason why I can't know color and flavor for my electron. In fact, color and flavor are, how do I want to say this? Color and flavor are the equivalents of two different directions. We can't measure color and flavor, and we can't measure Lx and Ly together, or Lx and Lz. Turns out the math is exactly the same. So this is our limit, is that we can only basically know two things about the angular minimum: the direction along one coordinate and its length. So remember I said that we like in chemistry the z-axis. So by notation, we always choose this combination, Lx and Lz. So what is Lz? Well, Lz is just the component along the z-axis. Right, so I can measure that. Right, so then we have to ask the question, well, when we measure Lz, what do we get? Where can I put this? All right, I'll put it over here. And I'm going to draw a little box to put it right here at the bottom. This is my last point for the day, and then we'll be done. So now you have to ask the question, well, when I apply Lz to my wave function, my spherical harmonics, which is going to be Lz of, let me write it in the right letters, y, j, m. So when we apply Lz and measure the z component of it, we get h bar m times y m j. So what does that mean? So m, the quantum number m, specifies the orientation of the angular minimum with respect to the z-axis. Okay, so what does that mean? Well, if my angular minimum is in this direction, okay, then that means my rotation is clockwise. Using my right hand, my rotation is in the direction of my how I curl my fingers. Right. So if angular minimum is pointing this way, I rotate counterclockwise about it. Right. So the electron is precessing in a clockwise fashion around my proton. Well, what if I do it this way? Well, now the electron is precessing counterclockwise around my electron relative to the same axis. So L tells you something about the way that the electron precesses around the atom. And so if Lz, if the L was directly, so if the atom's z-axis is in this direction, and m is 0, which means it has no component along the z-axis, then what that means is that the electron effectively classically is orbiting around the equator of the system, like this. Right, it's orbiting around the equator of the hydrogen atom. Now it's not really the equator, it's three-dimensional. We have to be careful about that. This doesn't work exactly, but classically what it would mean is that the electron is orbiting the equator, and +1 would mean that the electron is precessing like a top around the z-axis. Right, so m equals +1 for this system would be the electron precessing around the north pole of the proton counterclockwise, or clockwise, that's this way. Counterclockwise above the north pole, and m equals -1 would be it precessing clockwise around the south pole. All right, so for j equals 1, there are three options. You can either precess around, say, what would you call that? The northern, what's the top line called? The tropic, the Cancer? I forget which one that is called. Precessing around the northern hemisphere, M equals -1 would be the southern hemisphere, and M equals 0 is precessing around the equator. Okay, so we'll look at that math more carefully. That's a classical interpretation. It's not true. We know what the trajectories look like. They look like spheres. They look like p orbitals. They don't look like precessions around an axis. We've got to adjust that a little bit. We'll look at that more carefully on Tuesday. All right, you guys have a good weekend.
Time to run and go give me some.